Let's talk a little bit about delocalized electrons. And we've touched on this a little bit in class when we talked about acids and bases and the delocalization of the negative charge of the carboxylate anion. So delocalized electrons are electrons that don't belong to any one particular atom or don't have to live in between two atoms if they're shared electrons. Delocalized electrons are electrons that are shared between three or even more than three atoms. If we can draw more than one valid Lewis dot structure for a molecule or ion that has the same connectivity, or in other words, the atoms are all connected in the same way, but the electrons are arranged differently, that species is said to have resonance or delocalized electrons. And the two different Lewis diagrams that I draw are resonance structures. The molecular ion is said to be a resonance hybrid of the two structures that are drawn. The actual structure is intermediate between the various Lewis structures that we can draw. None of the Lewis structures accurately reflect the true structure of the molecule or the ion. For instance, let's consider the carbonate anion. This is CO3 minus 2. The carbonate anion can be drawn in three different ways. We have negative charges on two of the three oxygen atoms. The neutral oxygen can be the oxygen pointing up, the oxygen pointing to the right, or the oxygen pointing to the left. These three resonance structures are equivalent because each one of them has a negative charge on each of two different oxygen atoms. However, their structures are actually different because the negative charges are on different oxygens. If any of these individual structures accurately reflected the true structure of the carbonate anion, we would expect to have two different types of oxygen atoms in this anion and two different carbon-oxygen bond lengths. We would expect to have one short double bond and two longer single bonds, or sigma bonds. What we actually find is that all three carbon-oxygen bonds in the carbonate anion are equivalent, and all three of the oxygen atoms have equivalent negative charges. So the carbonate anion is really an average of the three structures that we saw before. We need three Lewis structures to describe the real molecule. Two negative charges are distributed over three oxygens. All carbon-oxygen bonds have the same length. When we draw the double-headed arrow between structures of this type, that is meant to indicate that these are resonance contributors, or resonance structures. To the right, you can see that we have an electron density map for the carbonate anion, and all three of those oxygen atoms have the same degree of negative charge. So we have three oxygen atoms sharing two negative charges. Or in other words, we can say each oxygen has a minus 2/3 charge, and each carbon-oxygen bond is equivalent to 1 1/3 bonds. So let's consider the rules for drawing resonance contributors. First, every resonance contributor must be a valid Lewis dot structure. You cannot violate any of the rules that we talked about when we discussed drawing Lewis dot structures. You're only going to move electrons around. You're not going to move atoms. The only electrons that you're going to move are going to be from pi bonds or lone pairs. You never move sigma bonds because that means that you're going to break the connection between two atoms if you move a sigma bond. The total number of electrons does not change. Charge must be conserved. For instance, in our carbonate anion, all three of our Lewis dot structures had a -2 charge. If you start with a negative charge, you have to end up with a negative charge. If you start with a neutral species, you have to end up with a neutral species. Second row elements may not have more than 8 valence electrons. This is just another way of saying that you cannot violate the octet rule for second row elements, or that your structure must be a valid Lewis dot structure. However, keep in mind that your second row elements may have less than 8 electrons in the valence shell. Let's consider the nitrate anion, NO3-. You may remember that we did a Lewis dot structure of this. Nitrogen has a positive charge because it has 4 bonds. I have 2 oxygens with negative charges and 1 neutral oxygen. I can move these electrons around, and in doing so, I'm going to distribute that negative charge across all 3 of the oxygens. First, if I take a lone pair of electrons and push it in towards the nitrogen and make a double bond, then I'm going to have 5 bonds to nitrogen. Since nitrogen is a second row element, you know that I can't have 5 bonds to nitrogen, so I'll have to push a pair of electrons away. This gives me a new Lewis dot structure that has my negative charge distributed on a different oxygen. I can draw another Lewis dot structure in which I move a pair of electrons from the oxygen on the bottom left towards the nitrogen. And again, nitrogen cannot have 10 electrons in its valence shell, so I'm going to have to move a pair of electrons away. So I push a pair of electrons away, and that's going to be a pair of pi electrons, and I push it towards the adjacent oxygen atom. That gives me a new resonance structure that looks like this, in which I have the negative charge now on a different oxygen. I want you to make a note that the only electrons that I've moved around are electrons that are lone pairs or electrons that are from pi bonds. Remember that if I move a pair of electrons that form a sigma bond, that means I'm breaking the bond between those 2 atoms. And resonance structures must have the same connectivity, so I cannot break those sigma bonds. Here are a few examples of molecules and ions that we could draw resonance structures for, so I want you to go ahead and give it a try. Go ahead and pause the video and see what you can come up with for all 5 of these starting molecules or ions. Well, let's see how you did. Let's have a look at this first structure right here. You can see that we've got a couple of lone pairs of electrons, right here and right here. We also have some pi electrons right there. That's what we're going to want to be moving around. I want you to notice I really can't move a pair of electrons from the pi bond towards the adjacent carbon. And the reason that is that will give me 10 electrons in the valence shell of the adjacent carbon. And I don't have any place to move an extra pair of electrons away, so that's not going to work for me. What I need to do is take a pair of electrons right here and move them in towards the sp hybridized carbon. So let's give that a try. If I move a pair of electrons in here, this carbon right here is going to have 10 electrons in its valence shell. And you know that carbon can only have 8 electrons in its valence shell. So what I need to do is I need to take 1 pair of electrons and move it out and put it on this nitrogen. And this is what my new resonance structure will look like. Let's have a look at our second structure. I have positive charge on nitrogen, negative charge on nitrogen. Every one of my atoms has an octet of electrons. What am I going to do here? If I were to try to take one of these pairs of electrons and move it in between the 2 nitrogen atoms, then I'm going to have 10 electrons in the valence shell of my terminal nitrogen. So I can't do that. What I'm going to do is I'm going to take a pair of electrons from the terminal nitrogen and move it in. And this means that the internal nitrogen has 10 electrons in its valence shell. So I have to take a pair of electrons and give it to this carbon. And here is what my new resonance structure will look like. Our central nitrogen still has a positive charge. However, the negative charge has moved from the terminal nitrogen to the carbon. I want you to notice that in each of these previous resonance structures that we've drawn, we have conservation of charge on either side. So in our first structure, we have negative charge for both species on either side of the arrow. In our second structure, we can see that we had a neutral species. We have a plus charge and a minus charge. They add up to 0. And on the right, we also have a plus charge and a minus charge, adding up to 0. Let's see if we can draw a resonance structure for our third anion, which is the anion of nitromethane. And I think that you're probably getting the hang of this, and you can see that what we're going to do is we're going to take a pair of electrons from one of the negatively charged oxygens and move it in and make a double bond between the oxygen and the nitrogen. When I do this, now my nitrogen has 10 electrons in its valence shell, so I'm going to have to move a pair of electrons from the double bond and put it onto the carbon. And here is what my new resonance structure looks like. You can see that in our starting structure we had a positive and 2 negative charges for an overall charge of -1. In our resonance structure we have a positive and 2 negative charges, again for an overall charge of -1. Let's go ahead and have a look at the last 2 of our structures. Here we can see we've got a positive charge on this carbon, so carbon is electron deficient. It can accept a pair of electrons, and that pair of electrons can come from the adjacent nitrogen. So I move in a pair of electrons to make a carbon-carbon double bond. I don't have to move any electrons away because my carbon originally was electron deficient. And here's what my new resonance structure will look like. I started with a positive charge on carbon, and you can see that I have a positive charge on the nitrogen. So we have conservation of charge throughout. Our final structure is a neutral species, but I can still move electrons around. If I were to take a pair of electrons from the triple bond and move it in to make a double bond between the carbon and nitrogen, that's going to give me 10 electrons in the valence shell of this nitrogen. You know that nitrogen cannot have 10 electrons in its valence shell, and I don't have any place that I can move those electrons away to. This isn't going to work for me. What I'm going to do, I'm going to take a pair of electrons from the neutral nitrogen and push it in towards this carbon. Now the carbon has 10 electrons in its valence shell. You know that that's not possible, so I have to move a pair of electrons away, and I move a pair of electrons onto the adjacent nitrogen. In my starting structure, my carbon and my 2 nitrogens each have an octet of electrons. They're going to have an octet of electrons in my final structure. And here's what my final structure looks like. Now you can see I started with a neutral species. I've separated the charge. I have a plus charge and a minus charge. So overall, my molecule is still neutral. Now the first few resonance structures that we looked at were equivalent. Obviously, none of the resonance structures that I've shown you here are equivalent because they have different numbers of bonds, they have charges that are moving around among different atoms. So when the resonance structures are equivalent, each one contributes equally to the resonant hybrid. When the resonance structures are not equivalent, there's generally going to be one that's more stable than the others. So in the case of our first resonance structures, this structure here on the right is going to be the one that's the more stable, or the larger contributor to the resonance hybrid. In other words, I could say that the resonance hybrid looks more like the more stable of the resonance structures. And why did I choose this particular resonance structure? Well, the reason is if I compare the 2 structures, in the first one I have the negative charge on the carbon. In the second one I have the negative charge on the nitrogen. Well, nitrogen, you may recall, is more electronegative than carbon, and it's more willing to accept a negative charge. Remember that carbons do not like to be negatively charged. In our next set of resonance structures, I can say that this particular structure is the major contributor to the resonance hybrid for the same reason. The first structure has a negative charge on the nitrogen, whereas the second structure has a negative charge on the carbon. If we consider our third set of resonance structures, I can say that this one is the major contributor to the resonance hybrid for the very same reason. Negative charge on oxygen as opposed to carbon. Let's have a look at our other resonance structures. Here I can say that this resonance structure is the more stable of the 2. Even though nitrogen is more electronegative, it's less willing to have a positive charge. Notice that in the second structure, all of my second row atoms have an octet of electrons, whereas in the first structure, the carbon is electron deficient. Whenever you can satisfy the octet, you're going to have a more stable resonance structure. And in our final set of resonance structures, we can say that this resonance structure is the major contributor to the resonance hybrid. The one on the right is a pretty minor contributor, and that's because I've separated the charges. In my first structure, all of my atoms are neutral, but in my second structure, I've separated a positive and a negative charge. So whenever I can neutralize charges, That's always better. So how did you do?